fact that the conduits are run underground does not negate any derating rules. The National Electrical Code, or NEC, explicitly requires derating for underground raceways in Section 310.15b3. You are correct in assuming that the neutral is current carrying in a fluorescent lighting system. Therefore, you must consider the neutral current when calculating the ampacity of the feeders. According to Article 310 of the NEC, the maximum allowable fill for a conduit is 40% for conductors with an insulation temperature rating of 90 degrees Celsius. Therefore, you cannot run 400 kcmil conductors in a 3-inch conduit. Here are some alternate approaches. Firstly, increase conduit size. Use larger conduits to accommodate the conductors. For example, 400 kcmil conductors could be run in a 4-inch conduit. Secondly, install parallel feeders. Install multiple feeder runs to reduce the current in each conduit. For example, you could use two 3-inch conduits with two 400 kcmil conductors in each conduit. Thirdly, use THWN-2 conductors. THWN-2 conductors can be used at 90 degrees Celsius without derating, which would allow you to run 400 kcmil conductors in a 3-inch conduit. However, THWN-2 conductors are more expensive. Based on the information provided, I would recommend increasing the conduit size to 4 inches or installing parallel feeders to ensure proper derating and conduit fill. Let's delve deeper into these concepts, providing more detail to ensure a comprehensive understanding. When dealing with underground conduit runs, it's crucial to understand that the Earth's temperature can affect the conductor's ability to dissipate heat. The NEC provides specific guidelines to address this. Section 310.15b3 outlines the derating requirements for conductors installed in underground raceways. These adjustments are necessary because the Earth acts as an insulator, hindering heat dissipation compared to conductors in free air. To accurately determine the ampacity of conductors' underground conduits, you must consider the ambient Earth temperature, the thermal resistance of the soil, and the number of conductors in the raceway. The NEC provides tables that specify ampacity adjustments based on these factors. Remember that these adjustments are cumulative, meaning that if you have multiple derating factors, you must apply them sequentially. Now, regarding neutral current in fluorescent lighting systems, it's important to understand why the neutral carries current in these circuits. Fluorescent lighting often utilizes electronic ballasts, which can introduce harmonic currents into the electrical system. These harmonic currents, particularly the third harmonic, are additive in the neutral conductor in a 3-phase system. This means that the neutral conductor can carry a significant amount of current, potentially exceeding the current in the phase conductors. To account for this, the NEC requires that the neutral conductor be considered a current-carrying conductor when calculating the ampacity of the feeders. This often leads to the need for a larger neutral conductor than would be required in a purely resistive load situation. Conduit fill is another critical aspect of electrical installations. The NEC specifies the maximum allowable fill for conduits to ensure adequate heat dissipation and to prevent damage to the conductors during installation. Article 310 provides detailed information on conduit fill requirements. The maximum allowable fill is typically expressed as a percentage of the conduit's cross-sectional area. For conductors with an insulation temperature rating of 90 degrees Celsius, the maximum allowable fill is 40%. Exceeding this limit can lead to overheating of the conductors and potential fire hazards. Now let us consider the alternate approaches that were mentioned. Increasing the conduit size is a straightforward solution to address conduit fill issues. By using a larger conduit, you increase the available space for the conductors, allowing for better heat dissipation and reducing the risk of damage during installation. When selecting a larger conduit size, ensure that it is adequately sized to accommodate the conductors and any necessary pulling lubricant. Parallel feeders offer another viable solution. By installing multiple feeder runs, you reduce the current in each conduit, which can alleviate both conduit fill and derating issues. When using parallel feeders, it's essential to ensure that all conductors are of the same length, material, and cross-sectional area. This ensures that the current is evenly distributed among the conductors. The NEC provides specific guidelines for installing parallel feeders in Article 310. The use of THWN-2 conductors can also be considered. THWN-2 conductors are designed to operate at higher temperatures than standard THWN conductors. This allows you to run more current through the conductors without derating. However, THWN-2 conductors are typically more expensive than standard THWN conductors. Therefore, you must weigh the cost savings of reduced derating against the increased cost of the conductors. Let's elaborate further on each of these alternate approaches, providing practical considerations and examples. Increasing conduit size involves selecting a conduit with a larger diameter to accommodate the required number of conductors while adhering to the NEC conduit fill requirements. The NEC provides tables that specify the maximum number of conductors of a given size that can be installed in various conduit sizes. These tables take into account the conductor's insulation type, the conduit material, and the number of conductors in the conduit. When selecting a larger conduit size, consider the ease of installation and the available space for routing the conduit. In some cases, it may be necessary to use multiple smaller conduits instead of one large conduit to facilitate installation. Parallel feeders, as mentioned, involve using multiple sets of conductors connected in parallel to carry the load current. This approach can be beneficial when dealing with high current loads or when conduit fill is a concern. When installing parallel feeders, it's crucial to ensure that all conductors in the parallel sets are of the same length, material, and cross-sectional area. This ensures that the current is evenly distributed among the conductors. The NEC provides specific requirements for parallel conductors in Article 310, including requirements for conductor sizing, overcurrent protection, and termination. The use of THWN-2 conductors can be a cost-effective solution in certain situations. THWN-2 conductors are designed to operate at a higher temperature rating than standard THWN conductors, which allows for higher ampacity without derating. This can be particularly advantageous in applications where space is limited and it is difficult to increase conduit size or install parallel feeders. However, THWN-2 conductors are typically more expensive than standard THWN conductors. Therefore, you must carefully evaluate the cost savings of reduced derating against the increased cost of the conductors. In addition to these alternate approaches, it's also important to consider other factors that can affect the ampacity of conductors. These factors include the ambient temperature, the presence of other heat-generating equipment, and the type of insulation used on the conductors. The NEC provides detailed guidelines for adjusting the ampacity of conductors based on these factors. Always consult the NEC and other relevant codes and standards when designing and installing electrical systems. It's crucial to ensure that all installations comply with applicable regulations to ensure safety and prevent electrical hazards. To provide a more comprehensive understanding, let's consider a specific example. Suppose you need to install 400 kcmil conductors in a conduit to supply a 1200 amp load. The conductors are THHN and the conduit is installed underground. According to the NEC, the maximum allowable ampacity of a 400 kcmil THHN conductor in free air is 335 amps. However, when installed in a conduit underground, the ampacity must be derated due to the higher ambient temperature and the presence of other conductors in the conduit. The NEC provides tables that specify the derating factors for various conditions. Let's assume that the derating factor for this particular installation is 0.8. This means that the ampacity of each conductor must be reduced by 20%. After applying the derating factor, the ampacity of each conductor is reduced to 268 amps. Since you need to supply a 1200 amp load, you would need to install at least 5 400 kcmil conductors in the conduit. However, this would exceed the maximum allowable conduit fill. To address this issue, you could either increase the conduit size or install parallel feeders. If you choose to increase the conduit size, you would need to select a conduit size that can accommodate 5 400 kcmil conductors while remaining within the NEC conduit fill requirements. If you choose to install parallel feeders, you would need to install 2 or more sets of conductors connected in parallel. Each set of conductors would need to be sized to carry a portion of the total load current. Remember to consult the NEC and other relevant codes and standards to ensure that your installation complies with all applicable regulations. Now let's discuss the importance of proper grounding and bonding in electrical systems. Grounding and bonding are essential for ensuring safety and preventing electrical shock hazards. Grounding provides a low impedance path for fault current to flow back to the source, which allows the overcurrent protection device such as a circuit breaker or fuse to trip and de-energize the circuit. Bonding connects all non-current carrying metal parts of the electrical system together, creating a common ground potential. This prevents voltage differences from occurring between metal parts which could pose a shock hazard. The NEC provides detailed requirements for grounding and bonding in Article 250. It's crucial to follow these requirements carefully to ensure that the electrical system is properly grounded and bonded. Another important aspect of electrical installations is overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. When an overcurrent occurs, the overcurrent protection device trips and energizes the circuit, preventing damage to the conductors and equipment. The NEC provides detailed requirements for overcurrent protection in Article 240. It's crucial to select the appropriate overcurrent protection device for each circuit base and the conductor ampacity and the type of load being served. In addition to these fundamental concepts, it's also important to stay up to date on the latest changes and revisions to the NEC and other relevant codes and standards. The electrical industry is constantly evolving, and new technologies and practices are being developed all the time. By staying informed about the latest changes, you can ensure that your installations are safe, efficient, and compliant with all applicable regulations. Consider attending industry conferences, subscribing to trade publications, and participating in continuing education courses to stay abreast of the latest developments. In summary, designing and installing electrical systems requires a thorough understanding of fundamental electrical concepts, as well as a working knowledge of the NEC and other relevant codes and standards. By carefully considering all of the factors discussed above, you can ensure that your installations are safe, efficient, and compliant with all applicable regulations.